In this lesson, we are going to look at change, okay? So Newton, one of the fathers of calculus, had a goal to be able to calculate the rate of change at a specific moment. Now, you might wonder, there's something wrong with that question, inherently wrong with that question, because change happens over time, right? So how can you talk about change in a moment? And the idea of change in math comes from looking at the slope of a curve at a particular moment, or thinking about how the function changes as its x value changes. Suppose we consider the slope of a secant. A secant is a chord connecting 2 points on a curve. So if I have the coordinates of 2 points on a curve, and you can see here, this is, I'll call this ordered pair number 1 over here for this point, and ordered pair number 2 for this point. I know that slope, the general formula for slope, is y2 minus y1 over x2 minus x1. And if I use the points I have here, the slope of my secant would be, let's call this y2, f of x plus h minus f of x divided by, that's y1 over here, x plus h minus x. So this would be the slope of the secant chord, rather, that I have drawn here. Okay, where I have 2 points, one at x here, and then one with an x value a little bit greater than that, and we would call this distance between those, in our problem, we've called this h. So if this is x here, and you add h to it, this is x plus h. Now, what we want to do is, remember, our goal here is to look at the rate of change at a particular moment. So let's say we are trying to figure out the rate of change at x. I might say, well, the slope of the secant chord, that actually gives me the average rate of change over this interval. Okay, the average slope at points along that interval. But what if I wanted to find a better estimate for the slope at x? There's an idea that we've learned in calculus that allows us to do this, okay? And what we want to do is, instead of using this secant chord, maybe I'll use a different secant chord. Maybe I'll use the secant chord there. Or maybe I'll use this secant chord. That might give me a better estimate. What would give me an even better estimate is to take this point and bring it closer and closer to the point where x is. To bring these points infinitely closer together. And what concept that we've learned in calculus allows us to do that? That is the idea of a limit. And we had to learn limits first in order to learn what we're about to here, because we want to bring these 2 points infinitely close together. And then when the points are infinitely close together, we want to find the slope between them. Or in other words, we want to find the slope between 2 points as the distance between them approaches 0. So let's recall for a minute an idea that you learned in geometry, and that's the concept of a tangent line, a tangent to a curve. Here are two examples of tangent lines. In the first diagram, we've got a tangent to a circle. And if you remember from geometry, when you have a tangent to a circle, that tangent is always perpendicular to the radius. And then in the diagram on the right, that is a tangent to a parabola that you see, meaning it touches the parabola in exactly one place there. Okay, so let's take that idea and go back to our secant chord. So here's a picture of our secant chord the way we had it. I think maybe the points were, let's see, something like that. And let's imagine that our point A is where X is. So I've calculated the average slope here. The slope of this line, which contains our secant chord, is 1.11. But remember, our goal is to calculate the rate of change at point A. And so what we want to do is we want to bring these points, I want to bring point B closer to point A. I want to shrink the distance between points A and B. So there we go. And what I want to do is I want the distance between these 2 points to approach 0. And if the distance between these 2 points approaches 0, my tangent line, my secant line, this is called a secant line that contains a secant chord, then becomes a tangent line when the distance between those 2 points is 0. So you can see I've got point B literally on top of point A. And the slope of this line at this moment is what I'm looking for. My secant line has gone from being a secant line to being a tangent line. And that's what we're looking for. We're looking for the slope of the tangent line to give us the rate of change at that moment where X is A. The idea, this concept of an instantaneous rate of change that Newton studied is called the derivative, okay? And as I just talked about, you want to shrink the distance between 2 points so that the distance between them approaches 0. And we want to find the value of the slope as that happens. So remember, I had just calculated the slope of the secant line for you a few slides ago, and here is the equation that we had, f of x plus h minus f of x over x plus h minus x. Now, of course, in the denominator, when you simplify this, that denominator is just going to wind up equaling h, because you have x plus h minus x, which is going to be h. So here, what we have is what's called the derivative, the instantaneous rate of change. And remember, in our original picture, what we saw 2 points whose x values were separated by a distance of h. This distance is h. And so if we want those 2 points to become infinitely close together, what we do is we take the limit as h approaches 0. Take the limit as the distance between these 2 points approaches 0, and that gives us what's known as the derivative of the function at a particular point, or the rate of change of the function at a particular point. And that is what we have in the box here. We have the formula for the derivative of a function. There are many different forms of this. This is probably the form that you will see most commonly. The derivative equals the limit as h approaches 0 of f of x plus h minus f of x over h. So conceptually, the derivative is a formula for the slope of a tangent line. The formula for the slope of the tangent line at a particular point on the graph. So if I have a graph and I have a point on that graph, I can draw a tangent line, which would look like that, and the derivative will give me the slope of that line. And it measures the rate of change at that point on the curve. Measures the rate of change at that point on the curve. So for example, things that we will investigate when we look at real-world applications of the derivative are perhaps the speed of a car or how quickly water is flowing into the bathtub. The slope at a point tells us how the function is changing at that moment. So here I've got a list of different notations. I don't want you to worry too much about this. The ones that you're going to see the most are, like I said, this one here. That's the formula I just gave you. But there are other forms of the derivative. What you want to be paying attention to is that what you're taking the limit of is some form of the slope formula. So these are all some form of the slope formula. The bottom one here is exactly the same as the top one, except they've replaced h with delta x. Over here on the left are notations for how to write the derivative in math notation. So I'm highlighting the 3 most common ways you will see it written. I'll almost never see these bottom 3, but I just put them up there because they do exist, so you've at least seen them. But really the 3 that I've boxed there are the 3 that you're going to see the most. And you would read this one here, f prime of x, this is y prime of x, or dy dx, and that stands for the derivative of y with respect to x, the rate of change of y as x changes. It's very specific, telling you the variables in your function. All right, so now we're going to do some example problems. So what we want to do is we want to figure out how to find the derivative by using that formula, which again is up here in the box. Okay. All right, so we are going to find the slope of the tangent line at the graph using the definition of the derivative. So the derivative, or f prime of x, is the limit as h approaches 0 of f of x plus h. Okay, when you have something, when you change the argument in the function here, you replace x with x plus h. So everywhere I see an x, I am instead going to write an x plus h. So this was replaced with this here. Okay, now, again, look at the formula I have over here in the red box. So in the numerator, I have f of x plus h, 2x plus h minus 1. That is just this, f of x plus h. Then minus, and you want to be careful here, it's minus f of x, so that's the mere original function. You want to make sure you distribute that negative sign into the f of x. All of that divided by h. Okay, so now I'm going to distribute the numerator. So I have 2x plus 2h minus 1 minus 2x plus 1 over the denominator. All right, you can see that I have 2 x's that will cancel, and I have 1's that will cancel. So now I have the limit as h approaches 0 of 2h over over h. And now, if I do direct substitution, I'm going to get 0 over 0. So I'm going to cancel out those h's, and I get the limit as h approaches 0 of 2. And you should know that the limit of a constant is that constant. All right, so the slope of the tangent line at this point is 2. Now, find the equation of the tangent line. You need two things to write the equation of the line. You need a point, and you need a slope. Okay. Points come from the original function. Slopes come from the derivative. Again, in part A here, I found that f prime of x equals 2. Okay, that's what I found out in part A. So let's do this in order. First, let's find the point. The point on the graph where x is 2, I'm plugging this into my original equation, and I get 3. So my point is 2, 3. My slope, well, again, looking at the answer that I got from part A, it doesn't matter what x is. F prime of 2 is 2 no matter what. So here I have a point and I have a slope, point, slope, and I can write the equation of my tangent line. Unless you're asked to write it in a specific form, I'm just going to do point-slope form. Y minus 3 equals 2x minus 2. If you're asked to write it, for instance, in slope-intercept form, you can then multiply it out, and you'll get y equals 2x minus 1. Okay, there we have it. Let's do another example. Okay, so we have another derivative problem here, and we are going to find the slope of the tangent line using the formula, and then we're going to write the equation of the tangent line, and we'll look at what that means on a graph for this problem. So I think it's nice to kind of think about what does f of x plus h equal. Again, for f of x plus h, you replace the x that you see in the equation with x plus h. So here that would be x plus h quantity squared. And that would give me this part of the formula. Okay, so the derivative equals the limit as h approaches 0 of f of x plus h, that's x plus h squared, minus f of x, which is x squared, all over h. And if I do direct substitution, you'll see you get x squared minus x squared over 0, which is 0 over 0. So now I'm going to do something algebraic, and what I'm going to do is I'm going to FOIL what's in the parentheses here and see if that gets me anywhere. So when I multiply all of that out, I get x squared plus 2xh plus h squared, and then I still have the minus x squared at the end over h. So you can see I am going to be able to cancel out these x squareds, which is nice, and now I get the limit as h approaches 0 of 2xh plus h squared over h. And now you can see that everything is divisible by h. So I can divide everything by h, canceling out an h, and I'm going to get 2x plus h. And now when I evaluate the limit by plugging a 0 in for h, I'm just going to get 2x. So I have, from this work, I've figured out that the derivative is 2x. So you'll notice this is different from the last problem we did. There's an x in my derivative equation, and that means that the slope changes at different points on this curve. The slope depends on the x value of your function, whereas in the previous problem, the slope was 2 everywhere. The slope was the same everywhere. Okay, so now we're going to write the equation of the tangent line when at the point negative 2, 4. So I already have a point right here. Now I only need a slope, which I get from the derivative. So I want the derivative when x is negative 2, and I'm plugging that into this formula that we just found. When x is negative 2, my slope is negative 4. And so now I'm going to use the point and the slope to write the equation of my tangent line. And again, in point slope form, that is y minus 4 equals negative 4, x plus 2. I'm actually going to write it in slope intercept form so we can graph it quickly. Y equals negative 4x. This is going to give me a minus 8 plus 4. So negative 4x minus 4. Okay, what does that look like graphically? Let me show you on the graph of this function. So you can see here we've got a picture. F of x is x squared. That's the graph of this parabola in purple. We have point P shown, the point negative 2, 4. And we found the equation of this tangent line, y equals negative 4x minus 4, which is the green line that you see touching the curve at negative 2, 4, tangent to the curve at the point negative 2, 4, which is telling me that at this point, the rate of change of this function is negative 4. And remember that our derivative was 2x, so the slope of your tangent line changes at different points along the curve. So for example, when x is 1, the tangent line looks like that, right? Over here at this point, the tangent line is much steeper. Okay, so here, the slope of the tangent line, or the rate of change, depends where you are along the curve. Okay, so here we have f of x is 2 over x. Find the slope of the tangent line using the definition. Or in other words, we're going to find the derivative using the definition of the derivative. So plugging into the formula, I should also just f of x plus h, what is that going to equal? I'm going to replace x with x plus h in my equation. So that's what I'm going to be plugging in for this part of the derivative formula here. Okay, f prime of x, or the derivative, or the slope of the tangent line, equals the limit as h approaches 0 of 2 over x plus h, that's f of x plus h, minus 2 over x, which is f of x, divided by h. And you can see if I plug 0 in for h, I'm going to get a 0 in the denominator. So I'm going to do something algebraic here. So the first thing I'm going to do is I'm just going to get rid of the complex fraction, meaning I'm going to get rid of the little fractions in the fraction. So I'm going to multiply by x plus h, over x plus h to get rid of those. I'm going to multiply that in. Now, when I multiply to the first fraction in the numerator, the x plus h's are going to cancel. And I'm just going to get a 2x. When I multiply to the second term in the numerator, the x's will cancel, and I'm going to get 2 times x plus h. In the bottom, I'm not going to multiply anything out at all. I'm just going to leave it alone with the thinking that I'm trying to get rid of this h, which has been causing a problem by giving me a 0 in the denominator. So I'm just going to I'm going to leave it alone, not jumble it up with everything else. Now I'm going to distribute the numerator. I'm going to distribute the -2 into the parentheses there. So I'm going to have the limit as h approaches 0 of 2x minus 2x minus 2h over hx plus h. And I can already see I think I'm going to be successful in what I'm trying to do here. My two x's are going to cancel each other out, and I'm going to be left with -2h in the numerator. And now you can see I'm going to solve the problem of the h in the denominator because these two h's I can cancel out. So now I have the limit as h approaches 0 of -2 over x plus h. And now I can actually evaluate the limit by plugging 0 in for h. And I'm going to get -2 over x plus 0, or -2 over x squared. So I have found the derivative of this function, which is -2 over x squared. Our next problem is f of x equals root 3x. Now, a little, you want to be a little careful about your f of x plus h and make sure that you remember that you need, this whole thing is going to become x plus h. So let me write it out here for you. Don't just write x plus h, because it's going to be 3 times all of x plus h. All right, here we go. The derivative of root 3x, or f prime of x, is the limit as h approaches 0 of root 3x plus 3h. I think I'll just multiply out what we had there. Okay. Minus f of x, which is root 3x, divided by h. And again, if you do direct substitution, you've got that pesky h in the denominator, which is going to make the denominator 0 and cause you problems. So that's our goal, to deal with that h in the denominator by doing something algebraic. And now I'm going to use an old algebra strategy that you should be very familiar with, which is multiplying by the conjugate. So I'm going to multiply by the conjugate of the numerator, which is 3x plus 3h plus root 3x. Root 3x plus 3h plus root 3x. And again, just a little reminder, when you multiply conjugates together, a plus b times a minus b, you wind up with a difference of squares, or a squared minus b squared. Okay, so when I multiply this all out, again, I'm not going to touch the denominator. I'm going to leave the denominator exactly as it is, but I get root 3x plus 3h squared, which is just 3x plus 3h, minus root 3x squared, and then again, a root squared is just itself, and in the bottom, I'm going to leave this alone. okay? And you can see in the top, my root 3x's are going to cancel. And very similar to the last problem, I now am left with 3h in the top, and therefore able to cancel out the h's in my next step. So now I have, with my h's canceled, the limit as h approaches 0 of 3 over root 3x plus 3h plus root 3x. And now I can actually evaluate the limit and plug h in, 0 in for h, which is going to go right there. And I'm going to get 3 over root 3x root 3x. Oops, sorry, plus root 3x, which is 3 over 2 root 3x. Now, this can be simplified because I have a 3 and a root 3. So first, I want you to realize, well, let's just rationalize it sort of the old way, the old school way. I'm going to rationalize by multiplying by the radical in the denominator, and I wind up with 3 root 3x on top and 2 times 3x in the bottom. And now I can simplify these, okay? Oh, I think I made this a little bit more complicated than it needed to be. Let me back up just one moment and do this slightly easier. Okay, so recognize that this root 3x can be written as root 3 root x. And I did it that way because really the only thing I can simplify is these 3's. I'm going to leave the root x alone. And 3 over root 3 is just root 3. So this is root 3 over 2 root x. Okay? And so I wind up with f prime of x is root 3 over 2 root x. Of course, this could also be written as 1/2 this, but it's more commonly written in this form.